Okay, so today's big lecture is going to be finishing up section 4.4, moving on into section 4.5, 4.6, 4.7, rest of the book, why not? But we're now basically into the latter sections of chapter 4, and then after that, I'm moving on into chapter 5, eigenvectors and eigenvalues, but that will probably be next week. So, again, I want to remind you of this, because it's up here, because I did delay me putting it up on our Canvas site, which was, let me put the old student view up here, because you just had your test and we're about to give you guys your test back and stuff like that. But here's those awesome videos you keep wanting me to make. So I'm going to be finishing up section 4.4 today is vector coordinates, coordinate vectors, and then moving on. Again, I want to remind you also about the PALS program. Please go to that thing and then report back to me. Let me know how that sucker's going and stuff, how the PAL leader's working. But right now, we're at homework number 15. This is your online homework stuff. It is due on November the 17th, so you got a good week to get this thing done if you haven't started on it yet. And also your homework number 5, which is on sections 1.4, well, actually 4.1 through 4.4, okay? So which ends up basically the end of what we covered today. But I'm going to continue on 4.5, 4.6, and keep moving on. But I just kind of broke it up kind of halfway through the chapter so we can have another homework set done pretty soon as well. So just to let you guys know, you got your 2 homework sets, your classic online homework set and your traditional homework set. This one's due in class on the 17th. This one's, the online one is always due by 11:59 that particular night and stuff. So there you go. All right, so let's go back over here and go back here, and let's pick up where we left off. So let's do this, and hit the old autofocus on it, and here we go. All right, picking up where we left off. We said this, let beta be equal to B1 vector, B2 vector, Bn vector, and be a basis, and that's the key word right there, a basis for a vector space V. Then the coordinate map x to the coordinate vector x with the little pointy brackets around there, beta, coordinate vector here, from the actual vector x to the coordinate vector x relative to beta, is a one-to-one linear transformation from vector space V onto Rn. You know, we've been playing around with vector spaces and we're always in Rn, R3, R4, R2, R17, whatever it happens to be. But there are other vector spaces out there. So we introduced some last time like polynomials, Pn polynomials, there's a vector space right there. Continuous functions, we're going to be looking at a lot of these guys and viewing them as vector spaces and how they fit together and stuff like that. And they don't fit your traditional Rn mapping. However, the coordinate vectors do. Okay, so the coordinate vectors, the way we write them is Rn, and x is from the original vector space, whatever that vector space happens to be. V could be, everything from, P sub n, polynomials, to some continuous function, whatever I want to sit there and play around with in terms of my vector space. So a great example right here is this, and I kind of wrote this one out just so I can kind of follow along just to show you guys this. All right, so here it is. Let's talk about the vector space P3. Now, what does that mean, P3? This is your polynomials of at most degree 3. So the degree or the highest exponent on the polynomials is 3 or less, okay? So what do these things look like? They look like A0 plus A1t plus A2t squared plus A3t cubed, and you stop there because that 3 right there matches to that subscript. So I don't have a 4th degree or 5th degree, t to the 5th, t to the 6th. Don't have any of that stuff. We stop at t cubed, where the AIs are coming from the real numbers. Now we talked also about this thing last time. In terms of your polynomials, what is your quote-unquote standard basis? It is 1, t squared, t cubed, ... all the way up to tn, whatever that n is. In our example, n is 3, so it's a 1, comma, t squared, comma, t cubed. This is your standard basis for this guy. Now, so if p, and I'm p of t, because these guys are in terms of t, is an element of p3, then p of t is going to look like a0 plus a1t plus a2t squared plus a3t cubed. This is the standard form. And now I want you to compare this. This is the important part. Look, I want to write these things as vectors. Now, this class is called linear algebra. What's the first thing that we started doing in this class? Pretty much day one. We put up these systems of equations and we wrote them as what? Matrices. We like matrices. We like this block, row, and columns of number type stuff here. But I got this polynomial. How am I going to be able to write this as a rows and columns of numbers? Well, here's the trick. This theorem back here says this, that there is a correspondence. This is what you need for all these vector spaces. There is a correspondence from whatever vector space I'm playing with to the coordinate vectors, where remember what the coordinate vectors are relative to a certain basis. So just to show you this example here, here's P of t, a0 plus a1t plus a2t squared plus a3t cubed. Now then, if you look at this guy as a coordinate vector, all right, relative to basis b, the coefficient in front of the constant is a0. That's the coefficient in front of the 1. The coefficient in front of the t is a1. The coefficient in front of the a squared, in front of the t squared is a2. The coefficient in front of the t cubed is a3. So I could write this vector like this: a0, a1, a2, a3. Because remember, it's a coordinate or coefficient vector. And these are the coefficients. It's a0, it's a1, it's a2, it's a3. These are the coefficients in front of the constant, the t squared, and the t cubed. So I can write it like this, and you can be able to read this guy off, because this is the standard basis, and be able to figure out exactly what the polynomial is. But this is a polynomial. That's a royal pain in the butt, but we can write it like this, and that one-to-one linear transformation. So if you don't like things looking like this, we can write things looking like this, like you normally would, and it'll be easier for you to manipulate and do what you need to do on it. So, quote, here the coordinate mapping from P to the pointing bracket P relative to basis B, coordinate map there, coordinate vector, is a one-to-one linear transformation from P3, this is where the polynomial came from, on to what? Well, when you look at this, because of that constant term, and then t squared, t cubed, that's actually a vector in R4. So, we can think of the coordinate mapping as just a different way to write the original object, which is in this case the vector. So, if you don't like this vector, you can write him like this. Just a different way of writing him is the way you need to look at this coordinate vector. Now, this one should be straightforward because we're using the standard basis, 1t, t squared, t cubed. I could mess you up by making a different kind of basis on this guy. And that's where that code theory mindset that we talked about last time, about it's a little bit more tougher to follow along unless you know what the original basis was. And that's kind of like your argument for, okay, how is my code going to work? This is what this is going to break this stuff down to. So, let's keep going. So, you know I got an example because I teach you guys through examples. That's my goal in life here. So, it says this. Use the coordinate vectors to verify that the polynomial is 1 plus t cubed, 3 plus t minus 2t squared, and negative t plus 3t squared minus t cubed are linearly independent. So this example, what I'm trying to do here is trying to show you somewhat the importance of these coordinate vectors. Because these coordinate vectors, the way you need to look at it is maybe a different way to write the vector in something that's back to your happy place in terms of all the stuff we've taught you. So, with this one, okay, let me talk about this first. Main idea. Linearly independent. All right. Question for you. Let's see what you guys know, because your life depends on it. Exams will be in a month. All right. What does it mean to be linearly independent? How do you prove something is linearly independent? No, see, you're already in trouble there. You got the algorithm on the matrix stuff. I want the definition. What does it mean for a set of vectors to be linearly independent? And how do I show that a set of vectors is linearly independent? I mean, vectors may not fit in a matrix. I mean, look at that. 1 plus t cubed, 3t minus 2t squared. These guys don't fit in a matrix in the traditional way you think about them. You have to be thinking about them other ways. That's kind of the point here. But I want to know what linearly independence is. How do I prove 3, 4 vectors are linearly independent? What do I got to do? Or linearly dependent? What do I got to do? Is that what equal to 0? You're getting there, but there's something special. What is equal to 0? Wait a minute. What? Or let's call them C. A may be part of my thing here. How about C1 times your first vector plus C2 times your second vector plus C3. So this is what you need to think of. To show linearly independence, or linearly dependent for that matter, you have to show, for linearly independent, show that when you have this, C1 times vector 1 plus C2 times vector 2 plus dot, 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 plus Cn times vector Bn, and you set it equal to 0, or in this case, the 0 vector, if they're linearly independent, what's the deal? If they're linearly independent, what's going to happen? Definition, straight up. If you got this, and you show that when you set this equal to 0, then the C1 is equal to C2 equals C3 equals dot, 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 equals Cn, and they're all equal to 0. And I'll put the little all in there. They're all equal to 0. Then they are, math code here, what does Li stand for? Linearly independent. If they are not, if you can find just one of them, C5 is equal to 27, not 0, then they're called linearly dependent. The only way you get linearly independence from the vectors is when you try to set up the equation, which is, I know you're thinking of matrix here, but when you set up the equation with the C1 times your vector 1 plus C2 times the vector 2, dot, 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 and you set equals 0, you're solving for the C's. And when you solve for the C's, the only answer you get is what we call the trivial answer, which is they're all equal to 0. I mean, 0 always works. 0 times anybody is 0. Yes, 0 always works. But if that's the only answer you can get, then they're linearly independent. Otherwise, they're linearly dependent. So, with this idea, this is what we're talking about. Thus, for the set of polynomials are viewed as vectors, and this is a set 1 plus t cubed, 3 plus t minus 2t squared, and minus t plus 3t squared minus t cubed, to be linearly independent. I'll sit there and code my little linearly independent part. This is what I got to do. I got to do thus C1 times the vector polynomial 1 plus t cubed plus C2 times the vector 3 plus t minus 2t squared plus C3 times negative t plus 3t squared minus t cubed equal to 0. And then I want you to solve for C1, C2, and C3. This is what you got to do to show it's linearly independent or linearly dependent. If you don't get all zeros, then it's linearly dependent. But either way, this is what you have to do to show it to me. Does that make sense? How do you do that? Well, that's a pain. Well, you can do it by folding it out and combining like that. It's a real pain. But if we do this, use the coordinate vectors, okay? So, since, I'll put a big old or. There's another way you can do this. It'll give you the exact same results. Our goal, we got to solve for C1, C2, and C3 here. So, here we go. Since, we talked about this, what did I put in my little notes here? I want to make sure I use the same letters and stuff like that I did before. A0, okay. Since A0 plus A1t plus A2t squared plus A3t cubed was equal to this vector here, which was A0, A1, A2, and A3, okay? Going from this guy, and this is that coordinate relative to your standard basis here. These were my coordinates here. I could do this. What would 1 plus t cubed be equal to? What would its coordinate vector look like? Well, the constant is 1. There is no t. There is no t squared, but there is a 1 coefficient, t cubed. Does that make sense? What would 3 plus t minus 2t squared, what would that be as a coordinate vector? Well, there's a constant 3. There's a coefficient in front of the t, which is a 1. There's a coefficient in front of the t squared, which is a negative 2. There is no t cubed, so that would be 0. Does that make sense? And while I'm at it, let's do the third one. What would negative t plus 3t squared minus t cubed be, what would that be in terms of a coordinate vector? Well, there's good 0, negative 1, 3, negative 1. So you're writing them as coordinate vectors because they're your happy spot. They're just numbers in a column, okay? That looks like a vector, and that's what you're used to looking like a vector. But vectors can take all different kinds of forms, is my point. All right, so for testing, linearly independence, we have this C1 times vector 1 plus C2 times vector 2 plus C3 times vector 3 has to be equal to what we call the 0 vector, okay? And then we solve for the C1, C2, C3. And if they're all 0, linearly independent. If they're not all 0, linearly dependent. But instead of, because of that one-to-one correspondence, instead of using these polynomials and trying to do it like we did here and trying to group together like terms and then be able to solve all that stuff, I can do this. This would be same as C1 times, this is my first vector, it was 1, 0, 0, 1, plus C2 times my second vector, which is 3, 1, negative 2, 0, plus C3 times my third vector, which is 0, negative 1, 3, negative 1. And you're going to set it equal to the 0, but as a vector, in these coordinate vectors, it will be 0, 0, 0, 0. Now, does that look like something you've done before? And how would you solve that guy? And from there, you would go to your happy place of the matrix, which is 1, 0, 0, 1, and these are column vectors. 3, 1, negative 2, 0. 0, negative 1, 3, negative 1. You would augment it, or to just get you used to your terminology here, to 0, right? And then what do? We RREF it. We make that pivot, sweep down, make some zeros. Then make this a pivot, sweep down. Make this a pivot, sweep down. Make this a pivot, but it's 0, so it can't be a pivot. Then you take this last pivot, sweep up, last pivot, sweep up, last pivot, sweep up, and you go solve, and let's see what you get. Well, I'm going to save some time on this one, because this is more of a theoretical kind of a question here. So when I go RREF, I get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, augmented with 0, 0, 0, 0. This is what you get when you do the reduced row echelon form. Does that make sense? what does it mean? Remember, these represent your C's, C1, C2, and C3 augmented to 0. So 1 C1 plus 0 C2 plus 0 C3 equals 0. That means C1 equals 0, C2 is equal to 0, and C3 equals 0. Now, what does that tell me? All the C's are 0. What do you got? Therefore, three dots in triangle fashion, therefore, the polynomial vectors are linearly independent. Does that make sense? Did I lose you guys anywhere? Now, don't get me wrong, you can go back, and if you know your classic algebra and stuff like that, you can solve for these guys, and what you do is you would distribute the C1, you distribute the C2, distribute the C3, and then group together the constant terms with all the C's, the coefficient in front of the T's with all the C's, the coefficient in front of the T squared with all the T's, the coefficient in front of the T cubed with all the T's, and then you're back to actually writing a system of equations. You can go with matrices on that, but that's 4 more steps that I don't need to do, but I would have gotten the same answer. The C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0. Why? Because of that direct correspondence that we talked about a few seconds ago, that there's that, quote, one-to-one linear transformation going from one vector to the other vector in the Rn, and it's easier to look at stuff in that Rn. So if you don't like what your vectors look like, you can rewrite them with those coordinates and that standard basis, but you got to get the basis first. Does that make sense? Did I lose you guys anywhere? All right. So just to practice with these coordinate vectors, solve for this. A little small problem here, but just a good review problem here. Let V1 be equal to 2, 1, 0. Let V2 be equal to 1, negative 1, 3. And let V3 be equal to, I'm sorry, not V3, let X be equal to the vector 1, 5, negative 9. I want to let H be equal to the span of V1 and V2, where V1 and V2 is a basis for H, and we'll call that basis beta because that's the way God meant it. B beta is beta basis. Okay, there it is. So if X is an element of H, I want you to find the coordinate vector relative to this basis, B. Again, I'm trying to practice with you guys in terms of understanding the question. Because you know I'm going to test, our next test, and then the final exam, I'm going to put a question like this on there. And if you don't understand the terminology, again, this is introduction 2, so a bunch of definitions. You're going to sit there and not know what to do, what you're looking for on this thing. So, again, trying to describe in this guy. So, if X is an element of H, we're supposed to find X vector relative to basis B. And remember, we're supposed to find X vector relative to basis B, which would be a C1, C2, where X is equal to C1 times vector V1 plus C2 times vector V2. That's the idea right there. It's a coordinate vector, so you need coordinates. Another word for coordinates is coefficient out front. Okay, it's the coefficient. So here we go, rewriting this. C1 times V1 plus C2 times V2 is equal to X would be C1 times vector V1, which is 2, 1, 0, plus C2 times vector V2, which is 1, negative 1, 3. It's got to be equal to the X vector, and the X vector was this 1, 5, negative 9. Does that make sense, using my terms up here? Okay? What now? I would write this as an augmented matrix. 2, 1, 0, bracket there. 1, -1, 3, and then 1, 5, -9. It looks like this. So let me rewrite that because 2, 1, 0, 1, -1, 3, augmented, that's what I meant to do there, 1, 5, -9. So let's practice. What's your first move? All right, so you've already got it down, row swap. Row swap. And this is row 1 with row 2. Let's see, R1 and R2. So this would give me 1, -1, augmented with 5, and 2, 1, 1, and then 0, 3, -9. What's your next move? Sweep down. -2 times row 1 added to row 2, replace the old row 2. Remember, whatever row you add to is row you replace. So this will be 1, -1, augmented with 5. -2 times 1 is -2 plus 2 is 0. That was the point. -2 times -1 is 2 plus 1 is 3. -2 times 5 is -10 plus 1 is -9. And then I got 0, 3, -9. What's your next move? And it could be either moves. There's more than one way to do this one, but you'll get the result. It'll be the same. All right. Well, no, I wouldn't add. I would. How about this? Negative row 2. -1 times row 2 added to row 3. Replace row 3. Because they're actually the exact same. So this is 1, -1, augment 5. I got 0, 3, -9, and then I got 0, 0, 0. Basically, -1 times this plus this, you get 0. -3 times 3 is -3 plus 3 is 0. -1, 9 is 9 plus -9 is 0. Row zeros. Not done yet. What's the next move? Before I do that, before I sweep up, because I want to avoid fractions as much as possible, by multiplying it by 1/3. 1/3 row 2, 1, -1, augment 5, 0, 1, -3, 0, 0, 0. And then I got one more move to make. And that move is to sweep up. So all I got to do is just add a 1 and a -1 there. So add row 2 back to row 1, replace row 1 with it. And I end up getting 0, 0, 0 on the bottom there. End up getting 0, 1, -3. And sweeping up here we go. Just adding 0 plus 1 is 1. 1 plus -1 is 0. -3 plus 5 is 2. What is this going to tell me? Remember, this does represent an augmented matrix. My coefficients vectors are these columns C1 and C2. So what does this tell me? C1 is equal to 2, and C2 is equal to a -3, which means the x vector relative to this basis is equal to 2, -3. Does that make sense? And again, this is a great example of why you need this stuff, because we're talking about a subspace of R3. H is a basis for vector 1, vector 2 is a basis for H. H is a subspace of R3 because the vectors have 3 components in them. Okay? But we only got 2 vectors in this guy, so my coefficient vector is going to have, coordinate vector is going to have, quote, 2 components in it. Does that make sense? All right. Now, more stuff. Section 4.5, the dimensions of a vector space. Now, I talked a little bit about this last time, okay? But we're going to kind of really get into it this time. And it's kind of short here, but like I said, make sure you guys, the most important is understanding this particular material and stuff. Okay, so, section 4.5, the dimensions of a vector space. Theorem. If a vector space V has a basis, B1, B2, B3, out to Bn, then any set in V which has more than n vectors must be linearly independent. Big theorem. If a vector space V has a basis, V1, V2, B1, B2, all the way out to Bn, okay? So there's n vectors in a basis. Then any set V which has more than n vectors must be linearly independent. Excuse me, linearly dependent. It's got to be linearly dependent. Why? That's my question to you. Why? Well, it should be obvious if you start looking at I got n components, and I got more than n vectors in it. Well, then I got way more vectors than I need. Yeah, but why, and what does that actually mean? All right. So, this is kind of a generalized proof, if you will. So let's start with what I call step number 1. Let's set ourselves up. Okay, let's say we have a set of vectors. We'll call them U. U1, U2, out to UP. Okay? Where P is bigger than N. What that means is the set has, okay, more than n vectors. Okay? Now, this isn't a basis. This is a basis. Okay? So let's look at the coordinate vectors. So, since beta, which is equal to B1, B2, to Bn, is a basis for vector space V, then we can look at U1 relative to basis B, U2 relative to basis B, UP relative to basis B. Each one of those, each one of these vectors can be written as a coordinate vector. Okay? Okay, and so we can look at this set of coordinate vectors. Okay? Now, here comes, so let me underline this. This is step 1. Here comes step 2. For each of these guys here, I'm just going to U sub I relative to beta. Each one of these guys here, I just pick one, call him I. This is a vector in R who? What space would this come from? R1. Not 3. N. Why R N? Because there's n vectors on these guys right here. And remember we talked about this with n vectors, and this is the coefficient, right? The coordinate vector, which is the coefficients. So we're talking about this guy right here, because, let me just do this so you can see this, because ui relative to b is equal to the vector c1 dot 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 out to cn, where the ui vector is equal to c1 times beta 1 plus c2 times beta 2 plus dot 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 plus cn times beta n. It's the coefficients, right? And there's n vectors, so there's got to be n coefficients. That means you're coming from Rn as these numbers put into this column vector. Does that make sense? Again, trying to tie all this stuff in for you guys. This is why. These guys just writing all the C's in this particular fashion here. Okay? But there are p greater than n of these ui beta coordinate vectors. Okay? There are p of these guys, because all the way out through VP there. There are 3 of these guys, p of these guys. Okay? Well, what does that imply about ui beta, u1 beta, sorry, u2 beta out to up? See, now we're back in our happy space of Rn. Each one of these vectors has n components, right? And how many of them do I have? P of them. So if you wrote this as a matrix, what size would he be? These are column vectors. Oh, there's no m in here. There's only p's and n's. What size would it be? All right, row by column. So rows, they're going to be n rows by p columns as you put these guys into each one of these little spots without having to draw it out. Hopefully you can see that. It's going to be n by p. Okay? And to figure out what these coefficients are going to be are, okay, in terms of this guy, if you're trying to row reduce this type of thing or whatever, again, proving this linearly independent, well, we'll go into this part right here, but automatically, this tells me something other. N by P, and P is bigger than N. If you try to row reduce this thing, what's the maximum number of pivots you could possibly get? How many? N. The maximum number of pivots I can actually get would be N pivots. You got N by M. You got either the pivots are going to show up in the rows or columns, but you're going to put the pivots here, right? You may have a row of zeros, I'm not sure about it, but whatever. But at most you're going to have is going to be, because this is N rows and P columns, you're going to have some guys over here left over that won't get any pivots in there, right? What do you call that? Linearly what? Dependent. Well, why is it linearly independent? I don't understand. Well, if you set it equal to 0, and you're solving for the C1, C2, C3, and you actually have, quote, more variables, more coefficients, than equations, there's going to be some guys left over that's not going to be able to be a pivot. These will be what? Free variables, and so they get to move on the other side, and so with these free variables, you get automatically linearly what? Dependent. Okay, I can't have free variables. That's called linearly dependent when we do that kind of stuff. Okay, but another way of looking at that would be, just a little side note here, I could go on to step 3 if I actually try to prove this to you guys. We can find, this was the idea I was trying to get across here, a C1, C2 out to CP, not all zero, because that's what's going on over here, not all zero, because there's a couple of rows left over that never got a pivot into them there, okay? Not all zero, such that C1 times vector U relative to the basis B plus C2 times vector U2 relative to the basis B plus dot 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 plus CP times UP relative to basis beta there, okay, is equal to the zero vector, okay? So, in other words, step number 4, the coordinate mapping is a linear transformation. Again, trying to tie all these things together here for you guys. A linear transformation, C1 times vector U1 plus plus CN, CP, sorry, CP times vector UP, and there's you of those guys, is a relative to basis B is equal to 0, okay? Which really implies that the C1U1 plus C2U2 plus plus CPUP is equal to 0, okay? And this is the same thing as 0B1 plus 0B2 plus plus 0Bn, because these are vectors, so they are linearly independent. So 0 times these guys, which really implies that the original vectors, U1, U2, all the way out to, sorry, I'm off the page there, all the way out to UP are linearly dependent. It's really a proof that I'm actually looking at here, but I'm doing more of a sketch proof on my logical argument here. But the reality is when you look at these matrices and you're trying to turn them into a matrix and you're trying to do the reduced echelon form and get those pivots in there, the only way you could be linearly independent is you have to have pivots on the diagonal, zeros off the diagonal, and you can't have any free variables on that thing. Anything below it better be row of zeros. So you can sit there and show you that C1 equals 0, C2 equals 0, that's your linearly independent stuff. I got way more columns, more vectors than I have actually basis elements and stuff, which automatically is going to make this guy linearly dependent, and that's what our theorem actually tells us and stuff. Okay. So, another one for you right here. Same idea. I'm not going to go into the great detail as I did on this last one. It says this: if a vector space V has a basis of n vectors, then every basis of V will also have n vectors. You can have more than one basis. Okay? Why? Is any other kind of basis will also have to have n vectors. You can't have more than n vectors, and you can't have less than n vectors. Why? Well, the only thing we really got going for us right now, because I'm talking about, eventually talking about the dimension, and I kind of showed my hand last time when you actually refer to a dimension, is the number of basis vectors, vectors in the basis type thing here. But the big thing that you need to know is this: basis vectors are what kind of vectors? Linearly independent. Basis vectors are always linearly independent. So, If I've got a basis vector of n vectors, a basis of n vectors, I know those n vectors are linearly independent, and everybody, any vector inside of V can be spanned by the linear combination of those n vectors. But thanks to that last theorem, if we got more than n vectors, we automatically know that's linearly dependent, right? And if you got a set of linearly dependent vectors, that can't be a basis because they got to be linearly independent on that guy. If you've got less than n vectors, right? Well, that can't be a basis either because everybody in V can't be spanned by those guys because it takes n vectors to be able to span everybody inside a vector space V. So you can't have more, you'll have linearly dependent. You can't have less because you're going to have a problem with the set of the span of the vectors have to actually cover, every vector has to be written as a linear combination of those guys, of the basis vectors. So that is really why. So from that, and I've already mentioned it, but now it's official, definition. Finite versus infinite. If V is spanned by a finite set, then V is a finite dimensional vector space. And the dimension of V, here it is right here. I put it in red, you guys can see this. The dimension of V is the number of vectors in the basis for V. And you can have more than one set of vectors that make a basis for any kind of set. That's the description thing that we're talking about in terms of disguising. You got your standard basis, but I can use the non-standard basis. That makes me work a little tougher, but it also makes the hackers work a little tougher too to try to figure out what my code is and how things are setting up. So, but the number of vectors in the basis must be consistent. It's going to be the same, regardless of which basis I use. And so the dimension of a vector space is the number of vectors in the basis for V. And little side notes here. If V is the trivial zero vector, yep, the zero vector is a vector space himself. It follows all 9 properties of the vector space. 0 plus 0 is 0, 0 times 0 is 0, everything that you want to do. The span of 0 is pretty much the zero vector. Okay, so this is actually a vector space. But we do especially note this. If you only got the zero vector, we say the dimension of V is actually 0 because that's so lame. We got to give it a number. We're going to call it 0. So you've got to have at least a non-zero vector in your vector space to get at least a dimension 1 out of it, okay? And here we go. If V is not spanned by a finite set of vectors, okay, then we call it having an infinite dimensional vector space. So we can have an infinite dimensional vector space. So in that particular example, we would write down the dimension of V would be equal to infinity. And we can have vector spaces that have infinite dimensional vector space, okay? Makes it real tough to actually talk about the basis and to do the systems of equation type thing on it, but we kind of focus our attention on the finite dimensional vector spaces, but you can have infinite dimensional vector spaces. For example, polynomials. If you notice, every time I talked about polynomials, I said polynomials at P sub n, we kind of cap it at some n value. What if we don't cap it? You know, t to the 1,327th power, okay, well, it's still a polynomial. I can write that stuff up, and I can just keep going out, dot, dot, dot. There's a pattern for these guys, but it will be what we call an infinite dimensional vector space. So, with that, let's talk about some examples of vector spaces and their dimension. Rn. The standard basis has n vectors in Rn, so the dimension of Rn is going to be equal to n. Remember, the dimension of a space is the number of vectors in the basis. How many basis vectors you got? Okay? All right, here we go. Complex numbers. A plus bi, where A and B are real. So this guy right here, A plus bi, complex numbers. The standard basis is going to be 1 for the real part and I, square root of -1, for the imaginary part. So officially, the dimension of the complex numbers is actually 2. Does that make sense? Because you got the real part and you got the imaginary part. That's your dimension 2. And then I threw down some p's on here. P2, the standard basis for P2 is 1t squared. So the dimension of P2 would be 3. If I talk about Pn, the standard basis would be 1t squared, t cubed, through t to the n. But because of that, so there's n vectors in there, plus that constant, one more, makes it the dimension of Pn is equal to n plus 1. But you understand, when you declare n, you can't have anything bigger than degree 312. There's no t to the 313th power is not allowed. So you cap it off. That's a finite dimensional vector space. But if you let it wide open, then P, without the little subscript, is a set of all polynomials. That will imply the dimension of P itself would be infinite. You have an infinite dimensional vector space. Does that make sense? All right. So don't think too deep in this. The dimension of a vector space is the number of vectors in the basis. The dimension of a vector subspace is the number of vectors in the basis of the subspace. With that being said, got to have an example. Here it is right here. Another great problem to do in terms of test questions and things like that. I want you to quote, find the dimension of H, a subspace of R4, if H is equal to the set of vectors that look like this. A minus 3B plus 6C for the first component, 5A plus 4D for the second component, B minus 2C minus D for the third component, 5 times D for the fourth component, where A, B, C, and D are real numbers. So please understand what I'm giving you. I'm giving you one vector with these little coefficients inside there, and I'm telling you I want to look at the space that this is spanned by type thing. Here, I want to know what the dimension of H, which is the vectors that look like this. Now, why is H a subspace of R4? Look at the vector. This is what you got to be inside of H. And we've written it as a vector. How many components is in this vector? 1, 2, 3, 4. That's why you're in R4. Okay? Well, how do I do this problem? Well, the first thing you need to do is you need to decipher this thing here and write them as vectors, or at least coordinate vectors. Let me show you. So H, if I rewrite this guy, would be equal to, now I'm going to rewrite this thing. I'm going to sit there and pull out the A, and let's see what the coefficients are. Remember, this is coming from R4, so I expect to have 4 components. A for the first equation or relation here, I got the coefficient is 1. For the second equation, the coefficient in front of A is 5. For the third equation, where's the A at? It doesn't have 1, so it's 0. For the fourth equation, there is no A in there, it's just 5D, so it's a 0. Does that make sense so far? Keep going. Plus, now let's look at the next letter, which is B. From the first equation component of my vector that represents the set H, what is the coefficient in front of the B? -3. On the second component, what do we got? No B's. Third one, we got 1, coefficient B in front of 1, and the last one is a 0. Plus C. Now let's look at C's. For the top component, we got a coefficient in front of the C of a 6. For the second one, we don't have a C. For the third one, we got a -2C. And for the last one, there's no C's. Plus D. For the first component, there is no D. For the second component, there is a 4D, so the coefficient is 4. For the third component is a -1, and for the last component, there is a 5. Such that A, B, C are elements of the reals. So I've rewritten what H actually looks like. That was the trick right there. Okay? So, what exactly is H? Now look at what I'm trying to do here. I'm going from the way it's written to understanding what exactly is a space. You guys should know the word space as the span. Very good. The span of a set of vectors. And the span is the linear combination of a set of vectors. And these are my linear combinations, A, B, C. These are my coefficients. So H actually is the span of the set of vectors of 1, 5, 0, 0, negative 3, 0, 1, 0, 6, 0, negative 2, 0, and 0, 4, negative 1, 5. Does that make sense? But wait. Is this a basis? 1, 5, 0, negative 3, negative 0, 1, 0, 6, 0, negative 2, 0, 0, 4, negative 1, 5? Is that a basis? Just because you span, it's all the linear combinations. What's the definition of a basis? It's a minimum number of vectors I can have. It's got to be linearly independent set of vectors. All I got is a set of vectors. Do I know if these guys are linearly independent? Yeah, actually I do. I know what the answer is. But you don't, okay? So I got to make sure it's linearly independent. Just because it's a spanning set, it is going to be a space, but that is not a basis. Not yet. I got to make it a basis. I got to make sure it's the fewest number of vectors that I need. I may have too many vectors here. I need to kill off the guys that are linearly dependent. So, to be able to be a basis, that's what I'm after on this one. For H, I want to check for linearly independence, which means it's linearly independent if C1 times this first vector, 1, 5, 0, 0, plus C2 times this second vector, negative 3, 0, 1, 0, plus C2 times the next vector, 6, 0, negative 2, 0, plus C4, that's a C3 there, C4 times the last vector, 0, 4, negative 1, 5, equals 0. This is how we check it, and it's linearly independent. Then, this is a basis, then the C1 has got to be equal to 0, C2 is going to be 0, C3 is going to be 0, and C4 is going to have to be equal to 0. So, got to check this guy out. So now, you can write this as a vector. Now, how would you solve that guy? Augment matrix. Beating to death a dead horse once again. 1, 5, 0, 0, negative 3, negative 1, 0, 6, 0, negative 2, 0, 0, 4, negative 1, 5, augment with 0, 0, 0, 0. And now, what would you do? Okay. Because of time, and I got other things to do, we're going to go magically off the calculator and go RREF on this thing. Let me show you what you get. When you do RREF, I got this. 1, 0, 0, 0, 0, 4 zeros there. I got 0, 1, negative 2, 0, 0. I got 0, 0, 0, 1, 0. And I got 0, 0, 0, 0, 0. I got a row of zeros at the bottom. RREF. What does the RREF tell me from a basis perspective? Linearly dependent. Outstanding. How do you know? Okay. Well, this is augmented. I should put that on there. So there's really 4 of these guys. Okay, but why is it linearly dependent? Again, tell me why. We got a free variable. How do you know you got a free variable? Be careful on that. I can make some weird dimensions and stuff on this one. It's not the bottom row. It's something else. What's that? we got 3 pivots. Now, remember, this original vectors had 4 components. The pivots tell you who you need. Where are the pivots at? Here, here, and here. And these were column vectors, right? So we have a pivot in the first column, the second column, and the third column. We do not have a pivot, first column, second column, the fourth column. We do not have a pivot in the third column, which means that third column is the free variable, which means we can ship him to the other side, which means, in terms of a basis, what do I really need? In terms of a basis, therefore, H is actually equal to the span of which vectors do I actually need? The ones with the pivots. The first one, the second one, and the fourth one, right? So it's these vectors here. 1, 5, 0, 0. -3, 0, 1, 0. And the fourth one, which is the 0, 4, -1, 5. So actually, H is this guy. And again, it's the first, the second, and the fourth one. The first, the second, and the fourth one is the one that I actually needed. Does that make sense? So now, so H was this guy here, right? The span of these 4 vectors, but this was not a basis. We eliminated the guy that we didn't need, and there it is down there, okay? And this is actually a basis for H. And please understand this, because I think a lot of people get confused by this. Listen to my words. Not everybody pays attention to exactly what I'm saying. This is a basis. There is more than one basis for any kind of vector space. Okay? So a lot of folks, sit there and say, John can't spell. And it's true, I'm a math professor. I can't spell, I can't read. Even though I got a degree in history, I just watch TV and watch stuff off that, so I got my degree in history. But that's all right, it's military history at school. All right, but with all the stuff that I have, and my kids are the same way, they're really good at math, but reading and stuff. My daughter's good at reading. My son, well, we're working on it. So people think I'm misspelling stuff. These words right here. What's the difference? One has an I in it, one has an E in it. We're math people. We can figure that part out. Okay. What's the difference? When I'm talking about a single set of a basis, we're talking about one basis. Even though it's several vectors, it's one basis. You use the I. But you can have lots of different bases. You can have basis beta, basis gamma, basis C, all the different bases. And when it's plural, you use an E. Sorry. So I'm not just being crappy with my handwriting, which I am, of course. But there is a difference between the two. Yeah.
So for this one, would there be only one basis? Or are you
No, right now, well, no, for this one, we're talking about finding a basis.
finding a basis?
So this is just one of them, of many.
There could be more than
There could definitely be more than one, okay? And but based upon the information that I was given, and these are, here's the big deal. I wrote these vectors as column vectors, right? And we put it as a matrix, but the vectors are column vectors. Now, let me put it right in your face here. What operation did you use to figure out which ones you actually needed? You did RREF. What does that actually stand for? Reduced row echelon form. We didn't do reduced column echelon form, which there is such a thing. We did the reduced row. Why? Because that's the button on the calculator. So we did reduced row echelon form. So because of that, all I can do is tell you that I need the first vector, the second vector, and the fourth vector. So I went back to the original set of vectors and earmarked the ones that I need to create a basis. I could now do reduced column echelon form and actually get them down to a standard basis, as many zeros in this thing as I possibly can. I could do it that way, but I haven't taught you how to do reduced column echelon form yet. So all I got is these vectors here. Pick the ones you need to make a basis. First one, second one, and fourth one. So this is a basis, but now here comes the big question here. What is the dimension of H? Fill in the blank, your life depends on it. Go. It's not an R or anything, it's a number. What's the dimension? 3. And why is the answer 3? There's 3 vectors in the basis. And whether I change the basis into something else, there's always going to be 3 vectors in this subspace H. Okay? I could change them up, use different vectors for them and stuff like that, but there's guaranteed the minimum number of vectors I can have, it's going to be 3. That's now a constant. Does that make sense? So please understand, H was a subspace of R4. Subspace of R4. So then there's 4 components in my vector. That's not the basis, that's just what this is a subspace of what vector space. I'm a subspace of R4, but what is the dimension of H is the number of vectors in the actual basis of a subspace, and that is 3. See, where a lot of people get all this mess confused is, well, this is R4. What's the dimension of R4? Yeah, it's 4. It's not just the fact that there's 4 components in the vector. What's the basis? Well, go with the standard basis. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. There are 4 vector bases. There's 4 vectors in the standard basis. That's why the dimension of R4 is the same as that power 4. But this one's a subspace. I got 3 basis vectors in H, so the dimension of H is 3.
So the reason, you said we have multiple bases, I can't remember what topic it was, but we was going over row vectors, I think.
Yep.
And when we did the row echelon form, I know we had like multiple bases.
Outstanding example. Exactly right. So we'll be getting that one. I've got one in the works here. We're going to be getting back to that. So right now I'm doing column space. I'm putting vectors in columns, and I'm doing reduced row echelon form on them. So when I do reduced row, I go back, figure out where my basis, my pivots are at, and I have to go back to the original set of vectors to earmark which one it's going to be, because I'm doing reduced row and I'm looking at the columns, and that doesn't match up. So the pivots just tell me where they're at. I got to go back here. However, if I looked at this as row vectors, go back into this matrix and look at them as row vectors, then if I look at them as row vectors, you see this first vector right here, second vector, and third vector. Forget the zeros type thing over here. Third vector and the fourth vector. You with me? So this is 4 vectors in here. Where are the pivots at? First row, second row, and third row. I kill off the last row, and I can either tell you this is the basis vectors, or I could, because we did reduced row, these are equivalent. I could use this vector, and this vector. So I just created 2 different sets of vectors that you could have. So 2 different bases. There's still dimension 3, because I got 3 components in the thing, but there's 2 different sets of vectors I could use as basis, and you can have more than that. This would be the standard basis, because it's the one that has the most zeros. That's our definition of a standard basis. That's why we like 1, 0, 0, 0, 1, 0. That's the most zeros you can chunk into anything. All right. Here it is, and I'm going to do my best at drawing it. I tried to draw it out here. I may draw it a little bit better for you guys in just a second here. Another example, and I'm focusing on now R3. Why R3? So I can draw it. Okay, I can't draw R4 and R5. People keep asking me about, especially when you teach Calc 3 and stuff like that, Calc 4. We only focus on R3, but you talk about, the 4th dimension and stuff like that. And a lot of people will go, well, what is the 4th dimension? Well, mathematically, we can have n-dimensional. That's what we're doing here. I got 7 dimensions, 8 dimensions, 27 dimensions. That's fine. You can't draw it out. It becomes mathematical after a while. We represent them with these matrices and these sizes and figure out what's going on here. But if you want to look at it from a physical perspective, all right, so you've got, somebody left their little thing up here. This is a 3-dimensional object, right? Okay. What would the 4th dimension be? Typically, one way, multiple ways of looking at the fourth R4 or 4 dimensions is this. Put a time element on there. So if you take this 3-dimensional object and move him through time, then you can mathematically come up with a fourth dimension. And thanks to modern day computers and stuff, you can kind of map that motion out type thing here. Does that make sense? So you get that sense of, you know, another component within your X, Y, and Z parts there. But after that, fifth, sixth, seventh dimensions, there's nothing you can do in terms of being able to see and draw that type of thing. Now it becomes all, you know, information about a particular concept going through space or whatever. All right, so here we go. I'm talking about subspaces of R3. What kind of subspaces of R3? All right, so here it is, your classic X, Y, Z, three-dimensional space here, okay? You can have, with R3, you can have 0, 1, 2, and 3 space, okay? Zero dimension space. To have the zero dimension space, that means you're only going to get the zero vector in there. This is that trivial vector. Remember, the dimension of the zero vector is 0. The only guy is the zero vector. The dimension of that is 0. And what does the zero vector look like? In R3, it's the 0, 0, 0 vector, which is just a dot at the origin. But it follows all the protocols of what a vector space can do in terms of its properties. It is a vector space, so therefore, there it is. The zero-dimensional vector space is a dot. You have a one-dimensional vector space. This is a subspace, only a straight line. Why? A one-dimensional vector space means we only have one vector in the basis. 1, 2, 3, something like that. So if I actually plot 1, 2, 3, go over x1, y2, up 3, and you grab yourself a vector, and from the origin, draw a line, and you can just basically keep going one way or go back the other way. A one-dimensional vector space is a straight line in R3. So you got this three-dimensional vector space here. It's this pin. That is the vector. You can go as far up or far down as you want to go, but you got to be on this line. That is a one-dimensional vector space. What is a two-dimensional vector space in R3 subspace? Two-dimensional subspace of R3 is any plane. It's going to have to go through the origin. Why does it have to go through the origin? Same reason why the line has to go through the origin. Part of your definition, which was on your last test, by the way, okay, part of your definition is this. What do you have to have a vector space or subspace? I believe that on the test it was subspace. What do you got to have a vector subspace? 3 things. What are they? Zero vector has to be able to be in there, right? Zero vector. The zero vector is the dot at the origin. So the origin, any kind of vector space, must be there. What else? The sum of 2 vectors in your space has to be inside your space. And any scalar constant times a vector inside your space has to be inside your space. Scalar multiplication, addition of 2 vectors, called closure in terms of that, and the zero vector. That's the definition of a subspace. It only has 3 parts to it, unlike the definition of what a space is. We went through that when we first started this section. There's like 9 things you could have going on here. All right, so you're going to have a plane, and it's got to go through the origin, and any 2 vectors coming out of the origin is going to be inside that plane. That is what a 2-dimensional subspace is. The plane could have been this way, could have been this way, whatever. And then, of course, you could have, R3, which is a 3-dimensional subspace is R3 itself. I mean, it's going to be something in this particular plane that's R3. So how many subspaces of R3? You're always a subspace of yourself, and you're going to have 2, 1, or 0. So there are actually 4 different kinds of subspaces because of that zero trivial subspace type thing here. So keep going here, and then I'll let you guys go. Theorem. Let V be a p-dimensional vector space, then any linearly independent set of exactly p elements, vectors, in V is automatically a basis of V. That's what we were talking about earlier. How many vectors, how many bases are there? If I got got a vector space and it's got dimension 5, and any 5 vectors that are linearly independent from the space is going to form a basis. So officially, I can have an infinite number of bases on this stuff. I can just keep rearranging them because they look a little different because I like one versus another or whatever. But they got to be linearly independent, and they got to have the exact same number of spaces and stuff like that. And then the last thing here is, this one, the dimension of the null space. I'll leave you with this guy. Remember, we're gonna go back to null space and column space. The dimension of the null space is gonna be the number of free variables. There's your connection right there of the equation AX equals 0. And the dimension of the column space is the number of pivots in A and RREF. And we showed you that just a few minutes ago. So these are two major formulas in terms of being able to know what the dimensions are. When you look at the dimension of a null space, you go ahead and do that reduced row echelon form, figure out the pivots, and the non-pivots, quote unquote, the free variables, the number of free variables is the dimension of the null space, and the dimension of the column space is actually the number of pivots, and when you take your column vector and do the reduced row echelon form. Study hard on this stuff, and I think Jacob's got something to pass back to you guys, and I'll see you guys next time.